All right, this is officially the last lecture. All right, we're first taking a look at 13.6, just introducing ourselves to the actual functions of sine and cosine, and kind of just a little bit of a refresher course on how the unit circle greatly impacts the sine and cosine values. All right, so we're given this angle, and it lies on this point, 2 radical 2 over 3, negative 1/3. And it lies on the terminal side of the unit circle. So the key word is this guy is lying on the unit circle. Because I am lying on the unit circle, I get to use the knowledge that the fact that the cosine is my x-coordinate and the sine is going to be my y-coordinate. The reason this is true is because the radius of the unit circle is 1. And so these values essentially are just going to reflect the adjacent or the hypotenuse side of our triangle that we would create. So the cosine of theta would be 2 radical 2 over 3. And the sine of theta would be our y-coordinate, which is negative 1/3. Okay? If you'd like a refresher as to why cosine and sine are your x and y coordinate, please go back to your unit circle lecture video. All right, this next example is also going to be a throwback to our previous content knowledge. If I'm looking for the cosine of 675 degrees, it might be helpful for me to figure out on my unit circle where do I end up if I continue to rotate. Because 675 degrees is greater than 360, I know I'm going to do a full rotation around the unit circle, okay? However, I do know that it's not going to be 2 full rotations because 2 full rotations would be 720 degrees, okay? And so this is actually going to be really close to 720 degrees, but it's going to end up in that 4th quadrant here, okay? So one of the things you can do is figure out how far away is 675 from 720, which would be 2 full rotations around the circle. So 720 minus 675, that's going to get me a difference of 45 degrees, okay? And so what I'm really looking at in this quadrant here is my 45 buddy, okay, which is going to be 315 degrees. And I want to know the cosine, which is the x value of 315 degrees. Well, cosine in the 4th quadrant is positive, and he's going to share the exact same cosine value as our 45 in the 1st quadrant, which is radical 2 over 2. Notice, no calculators necessary. I'm naturally picking it up from my unit circle. And one of the important skill sets for you to pick up on is the how I walk through that process. Now let's do the same for sine of negative 5 pi over 6. So because it is negative, I know that I'm going to be rotating clockwise. One observation, negative 5 pi over 6, well, I know that means we're not going to make quite a full rotation to the 180 mark because the 180 mark would be negative 6 pi over 6, okay? So I can figure out that the distance between those 2 points is a distance of pi over 6. So negative 5 pi over 6 means we're looking at our 30-degree buddy in the 3rd quadrant. No matter what, we know that sine is going to be negative in the 3rd quadrant, and we're thinking about the sine values of our 30 buddies. And the sine value of our 30-degree buddies is going to be 1/2. Therefore, the sine of negative 5 pi over 6, who's a 30 buddy, is negative 1/2. All right, what our last example in this section is getting at is eventually introducing you how to graph sine and cosine functions and what their shape really means in a real-world context here. So looking at our Ferris wheel example, we have the height given to us above the ground is varies periodically as a function of time. Well, that makes sense because when you're on a Ferris wheel, you're going up and down and up and down, and your height is dependent upon where you are on the ride. Consider the height of the center of the wheel to be the starting point, and a particular wheel has a diameter of 38 feet. Okay, that means if the diameter is 38 feet, that means that our radius, which is going to be half of 38, is going to be 19 feet. And it travels at a rate of 4 revolutions per minute. So that means every minute your Ferris wheel has gone around once, twice, 3 times, and 4 times, okay? Just to give you a little bit of a diagram. All right, so now we're supposed to identify the period of the function. Well, a period is how long it takes for it to make one full cycle, okay, aka one full loop. Well, if the Ferris wheel is doing 4 revolutions per minute, I need to figure out how long it takes for it to make 1 revolution. So if 1 minute is 60 seconds, a fourth of 60 seconds gets me that 1 revolution is going to be 15 seconds. So the period of my function is 15 seconds. All right, now we are asked to graph this Ferris wheel here, okay? One of the observations when we're graphing this Ferris wheel is the fact that in the question it told us that we're going to let the center of our axis be the middle. So right here in the middle, which is going to be our x-axis, is going to be the center of the wheel, okay? Because the total wheel has a diameter of 38, I believe it was feet, yes, 38 feet, that means the total distance that I travel is 38 feet. And if the middle is 0, that means my maximum value is going to be 19 and my minimum value will be negative 19. Okay, well that also makes sense because we talked about the fact that the radius will be 19. Okay, the other important piece of information for us to recognize is the fact that so our x-axis is representing time. Well, at 0 seconds, I have not traveled at all. So we're going to start at 0. Okay? Then the next important fact is to figure out how can I represent my height or how can I break this up? Okay? So I'm going to let each of my... Let's each represent, how many do I have? I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of these little boxes on the x-axis here. So I'm going to let 2 of them represent a distance of 15 units total. Okay, so then therefore this will mark 30, this is going to mark 45, and this is going to mark 60 seconds, okay? So a few pieces of information to recall. The distance between 0 seconds and 60 seconds represents 4 revolutions on my Ferris wheel, okay? And between 0 and 15, I should have made 1 full revolution. Therefore, if I start off at 0, at 15, I should return back to being at a height of 0. Another piece of information I can think about. So if I'm on a Ferris wheel, I'm going to draw a little image here, and I'm going up and then down and all around, okay? So this is a total cycle of 15 seconds. I'm going to reach the same height halfway through my ride, which would be 7.5 seconds in, so I'm also going to have a height of 0 at 7.5 seconds. Now, halfway between my 0 seconds and my 7.5 seconds, I'm going to reach this maximum height of 19 feet, okay? Well, halfway between 0 and 7.5 is going to be 3.75. And we're going to let our max value be right approximately here, 19. Right here. And so now we're going to start to notice I have a little bit of motion here. And then halfway between 7.5 and 15, I hit my low value, which is going to be negative 19. Okay. And again, this is me a little bit precise. And this process, this pattern is going to repeat itself because essentially what is happening is we're unraveling the Ferris wheel. Okay. So notice halfway again between 15 and 30, I'm going to hit this height of 0, essentially. And then it's going to keep cycling back and forth. Okay? Let's see if I can explain this in another way here, just to walk through it a little bit more. So this part in green that I have represents 1 full revolution. Now, it's not very circular, and I understand my graph is terrible. So the total height between 19 and negative 19 is a total height of 38, which represents the full diameter of the circle, okay? This height of 0 is just representing our starting value around the circle. And if I'm starting off at 0 seconds, all of a sudden it takes me 7.5 seconds to return back to that height. And so every 7.5 seconds, I should be hitting this value in the middle, which is why every 7.5 seconds I am hitting this guy. The next important thing is to recognize that this max height here. Notice that I only hit the max height once every revolution, whereas I was hitting the 0 twice during a revolution. And so every 15 seconds, one full revolution, I'm hitting this maximum value of 19. That's why there's a lot larger gaps occurring in this function. All right, so this is once again just an introduction to these concepts. In the next section, we're actually going to start to graph the trigonometric functions. But hopefully what you're recognizing is this circular shape created by the motion of a Ferris wheel.